what I really would like to point out in his CV, this is his engagement in the e-learning, especially the e-learning, the EPSI e-learning format he was building up. So it is not only teaching and doing building, so doing things. It's also really passing it on, spreading it out, and we really are thankful because was his work that it was not only the e-learning platform like normal teaching, it's also the lecture series he was building up. So go on the EPSI website, and there you will, among a lot of these presentations, you will find a very important keynote of Mike Schleiss, 2006 in Budapest, So, and we're thankful to Vortrag Bakhoum. We will have that, and you can not only listen maybe to these presentations, but also to a lot of other importance. So, the stage is yours.
Well, good morning, ladies and gentlemen. I'm very honored to be here. I'm very humbled to be here among these very distinguished engineers and audience. I'm very happy for Mike Schleiss for this great event, which is lots of participants. I'm very happy to be here also, to be speaking in honoring Mike Schleiss' great work. And my talk will be technical, but from the heart. So there are 4 H's. So the presentation will be, after the introduction, 2 main parts: obelisks from Egypt all over the world, sky bridge between 3 buildings in Cairo, and AI and structural engineering education if we have time. The first time I met Mike Schleiss, it was in September, October 1995, 30 years ago. It was a conference in Hong Kong about bridges into the 21st century. And I was very much impressed by his presentations of the Tin Cow Bridge in Hong Kong. There was lots of activities in Hong Kong at the time, building many bridges. And I think this bridge for me, and it's the most elegant, most efficient bridge in the world. I like it very much. You have everything in it. It's cable-stayed. You have suspension cables, and the pylon is supported by masts like ships. Just fantastic project, and I was very much impressed. And still am very much impressed by it. Now I'm going to show a slide, which I wanted to say it is the slide. But I thought maybe too much. So it's the key main summary slide for structural engineering education and practice. This slide Mike showed in the conference in Budapest in September 2006 in a keynote speech, Challenges Education, Conceptual and Structural Design. It summarizes in a very nice way the stages of structural design: conceiving, the concepts, modeling, structural analysis, dimensioning, and detailing. I use this in education, in graduate studies in particular, master students, and in my own thinking. And throughout the presentation today, I will try to show, to some extent, how this has affected the work I was involved in. So this slide comes from this presentation, this conference, and you can find it in the e-learning platform. If you just write Challenge It Education, the title of the presentation, and Mike Schleiss, IBC e-learning, you will get the presentation in slides and audio. You can listen to it. It's very nice. So now, we'll talk about 2 modern obelisks, but at the beginning, we need to know some history. Obelisks existed in Egypt. This is in Luxor in the south of Egypt. This is the Luxor temple. There existed 2 obelisks. And the obelisks were built by the pharaohs starting about 3,000 years ago. So they are 1,000 years younger than the pyramids. And they are trapezoidal shape, going from 40 meters. The longest, I think, is about 30 meters. And they are a symbol of the god, one of the main gods of Egypt history, Ra. And in the modern times, they symbolize like looking at the sky and hope. The second obelisk was moved to Paris around the year 1840, and it stands there in the Place Concorde. And many other obelisks were transported from Egypt to Rome, especially in the 100 BC till 200 AD, more or less. And then in the 19th century, some were transported to Paris, London, and New York. Just one thing to look here. The pharaohs, when they built the obelisk, it was on a small foundation. And when it was moved to other cities in the world, they are put on a pedestal so that you can see it from far away. Now, other than this still well-standing obelisks, many were destroyed by earthquakes. I'll show you why. This is the map of Egypt, and there is here the well-known fault and very high seismic activity in south of Italy, south of Greece, and south of Turkey. So earthquakes in this fault or between two plate boundaries affected the obelisks which existed in the north of Egypt. So in the south of Egypt, in Luxor, near Aswan, near the quarries of the obelisks, they still exist. In Cairo, there is one which still exists, but north of Egypt, they were destroyed like this. And the idea came in the last 20 years, instead of having obelisks like this in the desert, why don't we move them to some squares in Cairo and to make it visible to people. One of them will be put on a metro station. This is a metro station in the very center of Cairo. These are the walls of the station, the roof of the station. Initially, it was supposed that a lightweight structure will be put on this top slab. But the obelisk is about 120 tons, and this supporting structure is also very heavy. It was not possible to put it on the top of the station, so we have like a bridge-type structure. I'll show some details about it later. If the height here is 16 meters, the span between the supports is almost also 16 meters. This structure was conceived by one of my professors. Our role here was just design review and supervision of the work. Another one, apologies for the not very nice slide. I took it from PDF. Anyway, this is another slide, another obelisk. And a very bright architect, it's called architect Atif Muftah, Egyptian architect, looked at the obelisk and he showed that there is a cartouche in the middle. A cartouche is like the stamp of the king. It's like this symbols here, or this writing, hieroglyphic writing. It's on the base also. So you thought, okay, we will make it hanging or elevated obelisk so people could come and look at the stamp of the king in the bottom. It's King Ramses II. It's a very clever idea from the architect, but how to achieve it was a challenge for the structural engineers. Okay, this is more clear. Okay, so we'll start with the one with the elevated obelisk with seismic base isolation. As I mentioned, this is one of the obelisks still in Cairo, Heliopolis region. Now this is in London, in Paris. Basically, now this is a small foundation on the soil for the time of the pharaohs. Now it's elevated for showing up with this rigid structure, and the obelisk is embedded up here so it have its stability. Now what we want to do is to have it elevated on 4 columns so people can go beneath it. This is a 3D view from the architect at day, at night, and this is also the concept. People will go, look up, look at the stamp, and look down and look at the base which existed, this base. Okay. So now, instead of this, we need to do this. 4 columns, steel frame, steel columns, and then steel frame. And what's made the matter more complicated is that the obelisk, it's a square, but like 1/4 of it was broken since it fell many decades ago or many centuries ago. And we cannot increase the depth of this steel frame a lot. I think the architect didn't want it. Okay. It's very sensitive. The dimensioning of these elements is very sensitive. We have to respect the opinion of the architect because he wants to do something which is really innovative architecture and very nice. So we did the analysis. So this was the concept part. We did the analysis. And we found that there is a lot of bending. This is the first mode, the second mode, the third mode. There is a lot of bending when we do this. There is a rigid connection between the steel column and the base. And the steel column with this beam, it's like semi-rigid. Okay. So this is a schematic view about seismic base isolation. You can find it many places, but this was from the University of Manchester. So if you do a conventional structure, and lots of these developments are from Japan. Conventional structure, you will get bending in the columns, bending in the beams. But if you do a seismic isolation, the structure will move as a rigid body. So you can decrease increase the time or decrease the frequency of the structure significantly, and then you get much less seismic forces. Okay, and so this is basically from the brochure of the Maurer was the developer of this the bearings that we used. And if you look at the time history, the red one is the conventional. The black one is when you do seismic isolation. So instead of this, we have used this. We have the seismic isolation bearings here. And this is the shape of the housing for the stone and the seismic isolation bearings. When we talk about detailing now, you can see this 45 degrees here. It was meant to be because sometime in the future, they will need to change the bearings. So this is a detailing to make sure that the people who will be standing here will have enough space to inner the jacks to remove the bearings. And this mass also is very important because when you increase the mass of a structure, you increase its period of vibration, and then you get into less seismic force. So this was the concept basically. Have the structure, the steel frames, have the obelisk on top. People could go inside, have a look at the cartouche here, and maintenance people can go and change in the future. Okay, so instead of this structure, we got this one. Now, if you put a time history record for the analysis, you get here 1.5 G. Time history, we used El Centro as an example. It's about 0.3 G or 0.3 the gravity, like 3 meters per second square. Okay, so you get magnification here, and here it's more. If you put the 0.3 G, here you get almost 0.3 G. So the structure is moving at the same period as the earthquake. Bearing from the time history record here, it was very high. The black one, which is the input, El Centro, it's California. And now, if we don't have the base isolation, that's the response of the top of the obelisk. And if we have the seismic isolation, it's almost the same. So the colors red and green are obviously selected to show this. What was very important is the tilting, because if we don't have the base isolation, we get tilting in the obelisk. And the maximum difference in deformation between the top and the bottom was 4.7 centimeters. And between here and here is 0.4. When we do the base isolation, the structure moves much more. It moves much more, but the difference between the top and the bottom is only 1.2 centimeters, so it moves like a rigid body. Okay, so this was constructed. People are using it to look from the bottom. It's a nice photo opportunity, and at night also it looks very nice. By the way, this sits near the new Grand Egyptian Museum, which will be opened in a few weeks. This is how it stands. It doesn't sit. It stands here near the pyramids and near the Grand Egyptian Museum. Just a quick word about the Grand Egyptian Museum. You see it's like a rectangle, more or less. What was very nice about the architects who did the design, Shifu Peng and Rushin Hennigan, they had their office in Ireland. And there was a competition of 1,500. Maybe this is outside the presentation, but it's very important. 1,500 persons who presented their bids for this museum and managed by the UNESCO, 2003, and only one or two who presented this idea that instead of having a wall here facing the pyramids, they will have glass. And then people who are visiting these 6 galleries of the museum can look at the pyramids as their background. Very clever idea, and it has been constructed, and it's very well received. This is an exercise on conceptual design. This is very creative from the architects. But the structural engineers here were Arup, mechanical engineers were Bureau Happold, and we worked with Arup on this project. Now, we have looked at this. There is another task we want to build over metro station. So this is how it looks in the middle of Cairo. And as I mentioned, you cannot put the obelisk directly on the metro station, so we have to have this structure. Here it is, and this is the structure for it. At night, it looks very nice. Okay, and these are the beams which connect this structure to be on top of the metro station. 3D view. And here comes the detailing. The detailing between these beams and the ring beam was very complicated. And everything is important. Concept, the analysis, the dimensioning, and detailing. Also, the analysis, we had lots of discussions with the original designer. Do we have torsion or not in this location? And it depends on the assumptions in the modeling. Now, we come to the third part of the presentation. Near to this obelisk in the center of Cairo, there is this nice modern building under construction. So this is how it looked like. This is the TV tower in Cairo, built in the 1960s. There is a big development in this area, overlooking the River Nile, 3 towers, and the architect will connect them in the top by this structure. The towers are about 30 meters high. Okay, so these are the 3 towers connected by a structure on the top. It's about 100 meters above the podium level and about 120 meters above ground surface. So this is how it was originally conceived, to have 2 floors of apartments in this area, but then it was reduced to a more modest and more realistic structure where we have will be a walkway and maybe some of the equipment of the buildings will be put here, and then a ring like this to connect for architectural purposes. Okay, so now how we'll build this will be 3 separate trusses. Okay, but a very important issue is how to raise these trusses and construct them in the top of the buildings. But another issue also is the support structure. This is the 3 trusses. We will look at this one. The first approach would be just have a simply supported truss between the edges of any 2 buildings. Okay, but I was concerned that this is a high risk, and if this truss fails or if the columns fail for any reason, okay, this will be a disaster. Okay, so and then we have to achieve robustness. So the idea was, now if we do this, obviously we'll have compression in these supports, but we'll have tension in these supports. Then we'll have to think with the bearing companies how to handle this tension. I will finish in 2 minutes. But why this? The idea that is, if we lose a column or if we lose a support here, this tension support will become a compression support. So this structure will be designed for the issues of serviceability, and also in case of earthquake, the glass doesn't break, and for the ultimate limit state. But this structure without the support here and the support just at the edge, only for the accidental load case, and then doesn't fail and then to be repaired later. Okay, so redundancy, with having a structure more redundant, we achieve robustness. The last thing, just in 1 or 2 minutes, AI and education. I teach structural analysis. Mainly my issue is teaching structural analysis and bridge engineering as graduate course. So we asked ChatGPT example of a simple beam analysis withdrawing the problem. Okay? So this was the question. He did everything with the calculations. I was amazed at this. What will you do? What will okay, I am retired now, but what my colleagues will do in 10 or 20 years. We did a frame also. But what was really amazing at this is this. Here, these are like, we can say, quantitative analysis by the ChatGPT. You put a load, you compute the bending moment, you compute the shear, and you compute the bending moment. But here is different. This is a question about stability and determinacy and of beams and frames. This is a simple beam, hinge and roller, static case. If you rotate this hinge and make it horizontal, this beam becomes indeterminate because all the 3 reactions will meet at this point. If you make this on 2 rollers, it's stable only for the vertical loads and not for the horizontal loads. And I thought that the AI computer will not be able to solve it. But it did. First beam, it says stable and statically determinate. Unstable, you have a mechanism. Conditionally stable. I was amazed that the ChatGPT said conditionally stable. This is, if you can say, this is qualitative knowledge and not quantitative knowledge. And so this raises questions. I don't have answer, but this is questions. How advanced is the software that is available now for artificial intelligence? So maybe we can have a discussion about that in the break or later after we finish the conference. Okay, so in my presentation, I talked in the introduction talked about the very important slide by Max Schleich, and I think it should be very much widespread in education and to practicing engineers. 2 obelisks in Cairo, the Sky Bridge, and how to try to achieve robustness and AI in education. Thank you.
Amazed about the content is there. Do you have any insights in the use of the platform, and is it increasingly used or is it decreasingly used? Do we reach the audience it is made for?
It's a difficult question. Yeah, it was very highly developed till 2011-12, and then it went into a bit of a stagnant period, but it's picking up again now. And with Harsha as the president, maybe we'll see an exponential increase in its use.
I hope so. Thank you.
Some further questions?
Thank you very much for the interesting presentation. I'm curious about the connection between the obelisk and the slab underneath. How did you keep it intact and connect to the slab?
Steel frame with the several studs going from the steel frame into the granite of the obelisk.
Okay.
It's a complicated connection, so that's why we needed to decrease the force as much as we can.
Just a point about the base isolation that you had, the same thing. Is it that you use LRBs and then
Yes.
do they recenter themselves after an earthquake event, or do you have to go back in and recenter them?
It's a small width structure, so we're not very much worried about the recentering. No, it's not. It's lead rubber bearings. Yeah. I don't think recentering will be an issue because it's just a symmetrical structure, square structure on 8 bearings, so it will just readjust itself, hopefully. Okay. But if there is a permanent deformation, then they can just go and replace the bearings.
Replace them.
Yeah, I'd like to follow on the base isolation topic. Did you also consider the vertical component, the vertical seismic component for the tilt analysis?
Yes. You see, this heavy base was done mainly so that we don't have tension. If there is some tilting, then the base by itself has enough weight that it will remain always in contact with the lead rubber bearings. Because if you get a tension, we risk to have the tilting, But the other thing is that you might damage the bearings themselves. So this heavy weight is, the first function is to always make sure that we have compression, whatever is the load that we get laterally, and to increase the period of the structure so we get the reduction in force. The vertical, I think we did the analysis for the vertical component. I don't remember the results now, but I'm sure that we did it. But there isn't something significant about the vertical component which has changed something in the system.
Okay, thank you so much. Thank you so much for the very technical details.